Hey, what's going on, guys? Let's do this problem right here. The first question is asking a stationary siren emits sound frequency 1000 Hz and wavelength 0.343 meter. An observer who is moving toward the siren will measure a frequency f and wavelength lambda for this sound such that. So what is going to be the f and the lambda? So let's see how we can find that. First of all, the siren, look, let's draw this diagram. So we have a siren emitting sounds right here, right? And let's put the wave like this. So the wave of the sound, let's say, goes like this. So it's going to be going like this, right? And a man moves toward this siren. Okay, he's moving toward it. What's going to happen to the frequency? So as he moves toward this one, we know V is equal to F lambda, right? V is equal to F lambda. Therefore, F is equal to V over lambda. As he moves toward this one, what's going to happen to this wavelength? This wavelength is going to be decreasing. For example, if he reaches this point, all this will be eliminated, right? Only this distance, this wavelength. So as wavelength gets lower, frequency will increase. So we can say the f is going to be equal to f is going to be greater than the 1000 Hz as he moves towards this source, right? Towards this stationary siren. What happened to the lambda? Lambda is basically the wavelength, length of the one wave, right? They have given that lambda is equal to 0.343, but since the pattern doesn't change, just because he's moving toward it, it doesn't change. The pattern doesn't change, so it's going to be remains always the same, right? We know that wavelengths, the number of wavelength that's going to be faced by him is going to be decreases, but the length of the wavelength is going to be always remaining the same. So the lambda is going to be always equal to 0.343 meter. So it doesn't change. Let's do the next problem. The second question is asking a pipe that is 120 centimeter long resonates to produce sound of wavelengths 480 centimeter, 160 centimeter and 96 centimeter, but does not resonate at any wavelengths longer than this. Okay, so let's see how we can. So we definitely, like, according to this information, we know that first harmonic motion is right here. First harmonic pattern, right? So let's take an open pipe and see what happens. So whenever we have open pipe, we are going to have antinode at the end. So here we are going to have antinode and both end, and this is our first harmonic for an open pipe. And if you look at this, what is the wavelength right here? This is half of the wavelength, because full wavelength pattern is like this. This is just broken this one into half, right? This one, like, not a full wavelength. It's not going all the way. So we know that this is lambda by 2. Lambda by 2 is equal to 120 centimeter. Therefore, lambda is equal to what? 2 times 120 centimeter, that's equal to 240 centimeter. And if you check this value, do we have 240 centimeter right here? We don't have that. So therefore, this is not right for this question. So let's take one close end. One side is closed, other side is open. What's going to be the first harmonic? First harmonic is going to be antinode at the end, not in the closed end, right? So that's going to be the pattern for the first harmonic motion in closed one side closed pipe. This is going to be lambda by 4, because this is like a quarter of the wavelength, right? So quarter of the wavelength, that's going to be lambda by 4, and that is the length of this is 120 centimeter. So what is lambda? Lambda by 4 is equal to 120 centimeter. Therefore, lambda is equal to 480 centimeter. We have that value right here. But if you're still not sure, we can check again. Like, we can check the other second harmonic motion and see whether it matches with the other values. So what is going to be the second harmonic motion for this one? It's going to be, so one antinode passes, and we are going to have another antinode, second antinode. So that's going to be the second harmonic motion. And here we are going to have second harmonic pattern, that is second harmonic. This is going to be the second harmonic, and if you see, this is 3/4 of the wavelength, right? 3/4 of the wavelength, that is equal to 120 centimeter. And if 3/4 of the lambda is equal to 120 centimeter, then what is the lambda? Lambda is equal to 480 divided by 3, that is equal to 160 centimeter. And if you check this value, we have that value. And also you can go and check other one too, but we already know this is one closed end pipe, so that's why they are given open at one end and closed at the other end, and that's the answer for this question. And the third one is asking, as you stand by the side of the road, the car approaches you at constant speeds, sounding its horn, and here you hear a frequency of 80 hertz. After the car goes by, you hear a frequency of 60 hertz. What's the speed of the car? The speed of the sound on the air is 350 meters per second. Let's see how we can calculate this one. So first of all, in this kind of question, we have to use the Doppler's equation. So Doppler's equation is F observer equal to F source times V, that is velocity of the sound in the air, plus or minus V observer divided by V plus or minus V source. Let's take the first situation. So the car is moving toward this observer. The observer's velocity is 0. So this is always 0. This is 0. So we can completely eliminate this one right here, because observer is not moving, right? So observer is 0. So we can eliminate that one. F source, we don't know, it's not provided. But F observer is provided. The observer hears 80 hertz frequency. So we can put that one right here. 80 hertz equal to Fs times velocity of this sound. So let's keep it as V and put the values finally, right? So we only going to have V on the top because V observer is 0, so we don't have to put that. In the bottom we have velocity of the sound plus or minus. So this is the most important thing. This is the situation we have to decide whether to put the plus or minus. So let's see how we can decide that, right? So let's see how we can decide that. So we have velocity of the air and velocity of the source. Okay, now it's thinking time, right? When a car approaches a guy. So guy is standing still and the car is moving toward him. And it produces sound, right? Sound wave is going like this. So as the car moves toward this person, what's going to happen to this wavelength? It's going to be decreasing, right? Because the distance is going smaller and smaller, so it's going to be decreasing. What is the relation between frequency and the wavelength? We have this equation that V is equal to F lambda. So frequency is going to be equal to wave's velocity over lambda. So as the velocity as lambda decreases, if we divide any value by small value, the total value gets bigger. So this is going to be going up. Frequency goes up. So if I put what sign, that will make this frequency go up. Here it's negative, because if I put negative, that's going to be a small number, and that makes this frequency higher, right? So that's how we decide to put what's to put, like plus or minus. So in this case, this is minus, and let's say this is our first equation. And second situation is this car is passing this, going away from the observer. So at the time he hear the frequency, that's 60 hertz. And here also the observer is not moving, so V0 is going to be 0. Fs we don't know, that's not provided. And V is velocity of the sound. Let's keep it as V and put the value finally at the end, right? So in the bottom we are going to have V and Vs. And here again we have to decide what sign to put. So as the car moves away from the observer, what's going to happen to the wavelength? So if something is moving away, the distance is going to be increasing, the wavelength is going to be increasing, right? So what happened if the wavelength increasing? F is equal to V over lambda. When lambda is increasing, F is going to be decreasing, right? So we have to put a sign that makes this whole value decreasing. Here we have to put a plus, because if we divide this one by a biggest value, this is going to be decreasing. So that's how we decide to put what to put in the bottom, right? So we have now two equations. Now all we have to do is simply simplify and find the The question is velocity of the source, that is car, velocity of the car, and let's see how we can find it. So let's choose a different color, and what I'm going to do is I'm just going to divide the first equation by second equation, because that will get rid of this fs, frequency of the source. We don't need that, right? That's not a question, so we don't need to find that. We only need what is the speed of the car. So that's the only thing we have to find. So this is going to be 80 divided by 60. We can say 8 over 6, 0, 0 cancels. And the other side, fs cancel. We can eliminate that one. And v also cancels, because both of them, the sound of the air doesn't change. So v cancels. And this is, since I'm dividing by 2, since this is the bottom, this is going to flip around and go to the top, right? So v plus vs over v minus vs. So this is the thing we are going to have. Then we have 8 times v minus vs. I'm just cross multiplying. V minus vs. Then 6 times v plus vs. And if you simplify, this is going to be, I continue this one right here. So we have 8v minus 8vs, 6v plus 6vs. And if I bring the 6v to the other side, it's going to be minus 6v, and that's going to make it this one 2v. And the other side is going to be plus 8v, that's going to give us 14vs. So let's plug the values. 2 times velocity of the sound, that is 350, divided by 14 equal to vs. 2 times 350 is 750, right? 700. So 700 divided by 14 equal to vs. So 14 we know 1 over 2. So this is going to be 100 over 2. So we can say this is 50 meter per second. Therefore, the speed of the car is 50 meter per second. And that's the answer for this question. I hope you guys like this video. See you next time.